Imagine you have a set of LEGO instructions that tell you how to build a house. For a child to follow the instructions without looking ahead, each step must be clear. There must be only one way to continue at any point. In LL1, parsing the instructions are the grammar rules, and the child is the parser. The grammar must satisfy two main conditions so that the parser can decide the next rule by looking at just one symbol, the next input token. Number 1, no ambiguity. For any non-terminal A, the sets of strings that can start from each of its productions must be disjoint. In other words, two different rules for a must never begin with the same token. Number 2, no left recursion. A rule cannot call itself as the first symbol on the right-hand side. Otherwise, the parser would loop forever, like a child who keeps drawing a circle without moving forward. If these conditions hold, the parser can make a predictive decision with just one look-ahead token, which is why the class is called LL1, left-to-right scan, leftmost most derivation, one token look ahead. Explanation: computation of first and follow sets. Think of a dictionary that tells you what letters can appear at the beginning of a word. The first set is that dictionary for grammar symbols. For a terminal, a real word like plus or id, first is just the terminal itself. For a non-terminal A, first of A is the set of terminals that can appear as the first symbol in any string derived from A. Mathematically, we compute first using these rules until nothing changes. If X produces epsilon, the empty string, add epsilon to first of X. For a production X produces Y sub 1, Y sub 2 through Y sub K, add every non-epsilon symbol of first of Y sub 1 to first of X. If first of Y sub 1 contains epsilon, also add symbols from first of Y sub 2, and so on. If all yi can become epsilon, add epsilon to first of X. The follow set is like a list of words that can appear immediately after a non-terminal in a valid sentence. For a start symbol S, we always put the end of input marker $ in follow of S. For a production A produces alpha B beta, add every non-epsilon symbol of first of beta to follow of B. If beta can become epsilon or beta is empty, add everything in follow of A to follow of B. These two sets are the maps the parser uses to decide which rule to pick when it sees the next token. Imagine you are reading a story and you know which words can start a new sentence first, and which words can finish the current one follow. This helps you predict what comes next without reading the whole paragraph. For the grammar E produces TE prime. E prime produces plus TE prime or epsilon, T produces id, we get. First of E is the set containing id. First of E prime is the set containing plus and epsilon. Follow of E is the set containing $ and right parenthesis. Follow of E prime is the set containing $ and right parenthesis. Construction of the LL1 parsing table. Now we turn the dictionaries first and follow into a simple lookup table like a chess board, where rows are non-terminals and columns are terminals including $. Each cell tells the parser which production to use. Algorithms. Initialize an empty table M of A for every non-terminal A and terminal A. For each production, A goes to alpha. For each terminal T in first of alpha, excluding epsilon, set M of a T equal to a goes to alpha. If epsilon is in first of alpha, then for each terminal B in follow of A, set M of a B equal to a goes to alpha. If any cell gets more than one production, the grammar is not LL1, because the parser would not know which rule to pick. Think of a restaurant menu where the row is the type of dish, a non-terminal, and the column is the ingredient you have, a terminal. The table tells you which recipe to prepare. If two recipes appear under the same ingredient, you would be confused. The menu grammar is ambiguous. Example table for the arithmetic grammar, simplified. Columns id plus star left parenthesis right parenthesis $. Row E goes to TE primes. Row E prime for plus column goes to plus TE prime, for other columns epsilon. Row T goes to id T primes. Row T prime for star column goes to star FT prime, for other columns epsilon. Row F for left parenthesis column goes to left parenthesis E right parenthesis, for id column goes to id. Initialize, push the end marker $ and the start symbol S onto the stack. The input string ends with $ as well. Loop until the top of the stack is $. Let X be the symbol on top of the stack, A be the next input token. If X is a terminal or dollar. If X equals a pop X and advance the input match, otherwise error. If X is a non-terminal. Look up M of X, A in the parsing table. If there is a production X goes to alpha, pop X, and push the symbols of alpha onto the stack in reverse order, so the leftmost symbol ends up on top. If the cell is empty, report an error. When both stack and input show $, the string is accepted. Stack manipulation example. Suppose the top of the stack is E and the next input token is identifier. The table entry M of E, id equals E goes to T E prime. We pop E and push E prime then T in reverse order. The stack now has E prime on top of T. The parser will continue expanding T before E prime, which matches a leftmost derivation. Real-world analogy, think of a to-do list stack. When you finish the top task, you remove it and add new subtasks underneath, always working on the most recent top item. The algorithm is called predictive because the next production is predicted solely from the current input token and the top of stack non-terminal. Elimination of left recursion and left factoring. These are two grammar cleanup techniques that make a grammar L1 friendly, much like rearranging furniture so you can walk through the house without bumping into obstacles. 1. Removing left recursions. Problem: a rule like A goes to a alpha or beta is left recursive because it appears as the first symbol on the right side. The parser would keep expanding A forever. Solution: introduce a new non-terminal a prime and rewrite. A goes to beta a prime goes to alpha a prime or epsilon. Analogy: imagine a hallway that loops back onto itself. To avoid walking forever, you put a door a prime that leads you out of the loop. 2. Left factoring. Problem: when two productions of the same non-terminal start with the same prefix. For example, A goes to alpha beta 1 or alpha beta 2, the parser cannot decide after seeing alpha which rule to use. Solution: factor out the common prefix. A goes to alpha a prime goes to beta 1 or beta 2. Analogy: if two recipes both start with boil water, then you write a sub-recipe for the common part, and then branch into the different endings. Applying both transformations yields a grammar where the first sets of alternatives are disjoint and no left recursion remains, satisfying the L1 preconditions. Example: original grammar for expressions. E goes to E plus T or T. Left recursion removed. E goes to T E prime goes to plus T E prime or epsilon. Error detection and panic mode recovery in LL1 parsers. Even with a perfect grammar, programmers make mistakes. The parser must notice the error and keep going so it can report many errors in one pass. Error detection. When the parser looks up M of X and AN finds the cell empty, the current token A is not allowed after non-terminal X. This is a syntax error. The parser can immediately report unexpected token A after X. Panic mode recoveries. The parser discards input symbols until it finds a synchronizing token that is likely to start a new correct statement. Common synchronizing tokens are semicolon, close brace, or the end of input symbol. Debs. Discard input symbols A equals next token until it is in the follow set of the current non-terminal or is a synchronizing token. Pop symbols from the stack until the top of the stack is a non-terminal whose follow set contains A. After that, the parser resumes normal parsing. Analogy: imagine you are reading a story aloud. If you stumble on a word you do not understand, you skip ahead to the next period, a natural pause, and continue reading from there. The skipped part is ignored, but you still get the rest of the story. Panic mode is simple and works for LL1 parsers because the follow sets give us safe places to restart. Why not try to fix the error? More sophisticated techniques, phrase-level recovery error productions exist, but they need larger tables and more complex logic. For teaching and many compilers, panic mode is enough. Error reporting. Include line/column numbers the unexpected token and the set of expected tokens first or follow to help programmers locate the mistake. Example message syntax error at line 3 column 15 close brace. Unexpected expecting one of plus minus close parenthesis $. Time complexity. The parser reads each input token exactly once and performs a constant time table lookup for each step. Therefore, the running time is big O of n, where n is the length of the input, number of tokens. The stack operations, push and pop, are also big O of 1 per operation, and the total number of pushes and pops is proportional to the number of symbols generated in the parse tree, which is big O of n for a context-free grammar without excessive epsilon productions. Space complexity. Parsing table. If the grammar has n non-terminals and t terminals including $, the table size is n times t. In practice, many cells are empty, but the worst case space is big O of n times t. Stack. At any moment the stack holds at most the depth of the parse tree. For LL1 grammars, the depth is bounded by the length of the longest leftmost derivation, which is big O of n in the worst case, for example highly nested expressions. Typical programs have small depth, so average stack size is modest. First/follow sets. Each set stores at most t terminals, so total space for all sets is big O of n times t. Overall, the algorithm is linear time and uses space linear in the size of the grammar plus linear in the input length. This efficiency is why LL1 parsers are popular for simple languages and for teaching compiler concepts. A comparison. A bottom-up LR parser also runs in big O of n time but often needs a larger parsing table, states times symbols, which can be tens of thousands of entries for real languages, whereas LL1 tables are usually much smaller. Real-world analogies. Reading a recipe line by line linear time while keeping a small stack of current steps space. You never have to go back to previous lines, and you only need a modest notebook, the table, to know what to do next. Practical example: parsing arithmetic expressions with an L1 table. Consider the following simplified arithmetic grammar: operators plus in star parentheses and identifiers. Id rule 1e derives t e prime. Rule 2e prime derives plus t e prime or epsilon. Rule 3t derives ft prime. Rule 4t prime derives star ft prime or epsilon. Rule 5f derives open parenthesis e close parenthesis or id. Step 1. Compute first and follow shown briefly. First of e is id or open parenthesis. First of e prime is plus or epsilon. First of t is id or open parenthesis. First of t prime is star or epsilon. First of f is id or open parenthesis. Follow of e is close parenthesis or end of input. Follow of e prime is close parenthesis or end of input. Follow of t is plus or close parenthesis or end of input. Follow of t prime is plus or close parenthesis or end of input. Follow of f is star or plus or close parenthesis or end of input. Step 2. Build the L1 table: rows non-terminals, columns terminals, id plus star open parenthesis close parenthesis end of input. Table header: columns id plus star open parenthesis close parenthesis $. Row e, under id entry e goes to t e prime, under open parenthesis entry e goes to t e prime. Row e prime, under plus entry e prime goes to plus t e prime, under close parenthesis entry e prime goes to epsilon, under dollar entry e prime goes to epsilon. Row t, under id entry t goes to ft prime, under open parenthesis entry t goes to ft prime. Row t prime, under plus entry t prime goes to epsilon, under star entry t prime goes to star ft prime, under close parenthesis entry t prime goes to epsilon, under dollar entry t prime goes to epsilon. Row f, under id entry f goes to id, under open parenthesis entry f goes to open parenthesis e close parenthesis. Step 3. Run predictive parser on input id plus id star, id tokens, id plus id star, id end of input. Stack $e input id plus id star, id end of input action, use m of e with id goes to t e prime. Stack $e prime t input same action, use m of t with id goes to ft prime. Stack $e prime t prime f action, use m of f with id goes to id match id and pop. Stack $e prime t prime input plus id star id action, use m of t prime with plus goes to epsilon pop t prime. Stack $e prime input plus id star id action, use m of e prime with plus goes to plus t e prime. Match plus and pop. Stack $e prime t input id star id action, use m of t with id goes to ft prime. Stack $e prime t prime f action, use m of f with id goes to id match id and pop. Stack $e prime t prime input star id action, use m of t prime with star goes to star ft prime. Match star and pop. Stack $e prime t prime f action, use m of f with id goes to id match id and pop. Stack $e prime t prime input end of input action, use m of t prime with end of input goes to epsilon pop. Stack $e prime input end of input action, use m of e prime with end of input goes to epsilon pop. Stack dollar input end of input accept. Why does this work? The table guarantees that at each step the parser knows exactly which production to apply, because the first follow sets made the entries unique. The stack ensures we expand non-terminals before matching terminals, which corresponds to the natural order of evaluating the expression. This complete walkthrough shows how an L1 parser turns a simple arithmetic string into a valid parse, without backtracking, using only one token of look ahead.